Welcome to the first video. I'm going to start off with topic 6, which is rates of reaction. So that's all about what exactly is the rate of reaction, what things affect it, why they affect it, in other words the chemistry in how the things that affect the speed of a reaction happening, how they work, how on a chemical level, what is going on. And then it also covers why it's important to know about this from a scientific viewpoint. We're not just learning it for the sake of it, and it's got some real world applications that are very, very important, and we'll be covering all of those. But what we're going to start with in lesson 1 is we're going to look at how you measure a rate of reaction, what rate of reaction is. And we're going to touch on some practicals that you may have done in class. You may not have got the chance to do them with the COVID-19 outbreak, hopefully you will do, but we'll talk through them and the basics of those. Because these can be examined, they do get examined, and there are exam questions on these practicals. So it's really important when you are doing your chemistry lessons and you have got a practical, you don't just take that as a little bit of fun and a chance to go and have a chat and DOS with your mates. No, the practicals are really important. They can be examined. You're looking at things like the methodology, how you do them, the sources of error, how you can improve those, why the sources of error are there, the expected results, and also the analysis, things like, I'll cover this point many times because you see so many people making this mistake again and again, calculating the means from a set of results, mean average from a set of results. So you'll get 4 or 5 results in your exam from an experiment, and it will say calculate the average result, and it's worth 2 marks generally. They're not going to give you 2 marks for calculating a mean, because you should be able to do that while you're asleep without a calculator and hanging upside down from the roof. The reason why they're giving you 2 marks for that is because they want you to spot the anomalous result, which is the one that doesn't fit the pattern, the one that is completely out of sync with the rest of the data. If you can do that, you get this 2 marks. If you don't do that, you only get the 1 mark. But we'll talk more about that later. Anyway, on to the lesson. So as mentioned, we're looking at topic 6, the first lesson. We're looking at calculating rates of reaction. And in particular, what we're going to learn about is what a rate of reaction is, how and why it's important to be able to manipulate the rates of reaction, how we can measure those rates in experiments, and then how we can calculate the rates from those experimental results. So, first of all, what does the word rate of a reaction mean? You've probably already got some good ideas about this. You could also say like the rate of reproduction of a rabbit is different to the rate of reproduction of an elephant, and it's all about the speed at which that reaction happens. So something that's got a higher rate or a faster rate is a faster reaction. And some examples, so explosions and fire are fast reactions, they've got a high rate of reaction, whereas things like rusting are slow. A very good example of different things, of different rates in a reaction is, for example, the oxidation of glucose. Inside the body, this happens as respiration, and it takes the glucose, reacts it with oxygen, makes carbon dioxide and water. This is a relatively slow process. You can also do the same thing if you get some icing sugar and sprinkle it or blow it through a candle flame, and you'll see essentially a fireball being formed, and that is obviously a very fast reaction, but it's exactly the same reaction, just the rate is different. So there are lots of things that can affect the rate of reaction, okay, and we need to be able to understand this as scientists so we can manage the rate of a chemical reaction. If you're doing a big industrial synthesis to make a compound for, say, for example, a medicine or something like that, you don't want the reaction to go too fast because that could be dangerous and cause issues with health and safety. But then again, you don't want it to go too slow because that's going to hit your profit lines. So there we go, too fast. Pressure can build up inside reaction vessels if you're generating a lot of gas, for example, and that could lead to explosions. Or if you're doing it in the lab, you may have noticed this before, if you've chucked some magnesium inside some acid, it might bubble over the top, which isn't such a bad thing unless you're using very strong acids, in which case obviously you've got acid spilt everywhere. Too slow, less profit. So, the basics of measuring the rate of reaction. The first step is we can measure how long it takes to make a given amount of product. So obviously in a reaction, starting with our reactants, they react together, hence the name reactants, and they make the product, so they produce the products.
the other thing that we can do is we can measure how much time it takes for a reactant to be used up, which is significantly more difficult actually to do. And you can probably have a think about this if you're mixing two chemicals together. They both look like clear liquids, for example. How can you tell if that reactant's being used up? So you can infer that from the data, but it's very hard to measure directly. So next thing is we're going to come to some maths. The mean rate of a reaction is the amount of reactant used divided by the time taken to use it, or it's the amount of product made divided by the time to make that product. You need to be able to use these equations. It's quite easy to do. So obviously we're calculating a mean here. We're not calculating a instantaneous rate. That's something that will come later, we'll look at later and maybe in another video. But we're calculating a mean rate. So we take the amount of product that is being made and how long it has taken to make that amount of product. We divide those and we get our mean rate of reaction. The higher the number, the quicker the rate of reaction, the faster the reaction's gone. The more products being made in a certain time, the faster the rate of reaction. The shorter amount of time it takes to make a certain amount of product, again, a faster reaction. So, how can we measure this? How can we measure these things? So firstly, we normally either measure the mass in grams and how that changes, or we measure the volume in cubic centimeters or milliliters of a gas being produced. We can also measure the time it takes for a precipitate to form. Now we'll come on to a precipitate again later on, but a precipitate is essentially a solid that is formed when two solutions react. Okay, so two liquids react, two solutions react, they form a solid that's very, very fine solid, it's opaque, you can't see through it, and that allows you to measure the speed of a reaction. We'll look at that later on again. Okay, so there we go, precipitate, insoluble solid. The units of rate are normally measured in grams per second or centimeters cubed per second, because obviously if we've measured the change in mass per a unit of time, that's going to be in the unit of time is normally going to be seconds, so it's going to be our number of grams and how that's changed per second. Same for the volume of gas. Okay, it's just the basics of the maths there, and we'll look at that a bit more in a second. At higher tier, you will also be expected to calculate moles per second from these, or to be able to express it in moles per second if you're given the data in moles. It's very, very easy. Calculating moles is quite simple. There will be a video on that coming up later on. All you need to know really for that is the formula: moles is equal to mass divided by their relative mass. And so long as you've got that, which is topic 3, you should be able to calculate that without a problem whether you're sitting higher or foundation tier. So, the key experiments. These are the required practicals. You are expected to know about these for the exam. So the first one is how we can measure the change of mass in a reaction. Now, firstly, conservation of mass, the law of conservation of mass. It says that mass cannot be created or lost in a chemical reaction. So we can't create it, we can't destroy it. The mass of the products is going to be exactly the same as the mass of the reactants. That is a universal chemical principle. That is something that is always obeyed. You will never find the mass of the products being more or less than the mass of the reactants. It always will be exactly the same. So, how can we measure the change of the mass of a reaction then if the products have the same mass as the reactants? Well, it's useful when a gas is evolved. Now, evolved is a fancy word for saying a gas is made in a chemical reaction. It's the scientifically correct way of saying it. So you'll have seen this when you put things like magnesium or limestone chips in acid. You'll see gas bubbles, and those bubbles, as we say, is the gas is being evolved, and obviously that's going to escape into the atmosphere. So the first way we can measure the change in mass in a reaction when a gas is evolved is we can get our conical flask, for example, and you'll see my awesome art skills here, which my classes already know about. So I've got my conical flask where the reaction's happening. Inside the bottom I might put some marble chips, for example,
or some magnesium, and then fill with a certain amount of acid. At the same time, I'm going to do this on top of a balance, and that balance is going to give a reading of, say, 100 point, let's call it 0.07 grams. So this is at the start. So we're going to see some bubbles. So here we've got our marble chips. And here we've got our acid. And these are bubbles of gas. Now if it's marble chips and acid, it's going to be carbon dioxide gas. Then we're going to time it. So time after time, I'm going to come back and have a look at it. Can I do a better conical flask this time? What do you think? Oh yeah, look at that. Magnificent. So up here is just a bit of cotton wool to stop any liquid jumping out. Now our marble chips are a lot smaller and there's still some bubbles, and it now may say something like 0.97 point, say 5.1 grams. So we can see there's been a change in mass. Okay, so mass gone down, or reduction. It's equal to the amount or the mass of gas evolved. So obviously that gas is going to escape into the rest of the room, into the atmosphere, so it's no longer going to be sitting on the balance, it's no longer going to get measured. So that's experiment number 1.
Okay, so we can do that by capturing the amount of gas and measuring its volume. So we could do that with a measuring cylinder, or even better with using something called a gas syringe. And we're going to have a look now at what that looks like.
So there are 2 ways of measuring the volume of gas produced. Now, the first one, and the simplest one, although it's the one that you may not do in your science lab because it requires some specialist equipment, is using something called a gas syringe. And again, just like in the first one, we're going to use a conical flask for our reaction vessel, except this time, instead of putting some cotton wool in the top, we're going to put a rubber bung that's got a tube that comes down into it, a delivery tube, and then this delivery tube is going to carry on and it's going to go out at an angle and into a gas syringe, which is basically a giant syringe like you might see at the doctor's, except on the side we've got graduations for measuring our amounts of volume in millilitres or centimetres cubed. And again, we're going to get a timer, and we're going to time how long it takes. So we've got our acid, and again we've got our marble chips in there. So marble chips, acid, measuring cylinder. Oh, not measuring cylinder, sorry, gas syringe. Getting ahead of myself. Over time, what will happen is the gas syringe will have pulled back, the plunger, and we'll see somewhere on there, we'll see our reading. Okay, so we read this point. That's where the end of the syringe, the inside cylinder, goes to. And everything else is exactly the same. Our bung here with the delivery tube through it, and again smaller pieces there, and we can see that the gas has been evolved. This is good, it's quite accurate. We trap all of the gas this way and hopefully none of it escapes. There are some issues with this method though, and at my school, very cleverly, someone has tied a bit of wire around this part and hooked it onto the main part of the syringe, and that is because if the reaction happens too quickly, this plunger can go shooting out and can fly out of the back, and often these are made out of glass to make them accurate, and obviously if you've got some glass flying out it can break quite easily. So it's quite an accurate way of doing it, and we're going to look at the less accurate way of doing it next, which is what you will probably do in school and you may get asked questions about in the exam as well, and the way to improve it would, the one I'm going to show you in a second, would be to do it this way. Some issues you could get if this bung is cracked or the delivery tube has got some cracks in it, you can lose some of the gas, not necessarily all of it. Other things that can happen is these the plungers can get quite stuck if they're quite old, and then that means that the pressure of the gas builds up but doesn't push them back as quickly as possible. Instead you get high pressure inside there, which can affect your results as well. Okay, the most common way to see this done is with a water trough, which can just be a bowl of water, and an upturned measuring cylinder. And what you do is you fill the measuring cylinder with water, Step 1. Step 2 is you put your hand over the top of it and you flip it upside down and put it under the water. You have to do that very quickly and very carefully to try not to lose so much of this water. So, fancy word, invert it. I'm going to put measuring cylinder as MC and place underwater. The next step is we're going to take our delivery tube should have been a doctor with this handwriting. So the next step is you put the delivery tube into the measuring cylinder. And give myself enough space here. And the idea here is the gas, as it gets evolved, will come down the delivery tube and it will displace the water. The bubbles, as you can see, rise up the measuring cylinder. They push the water out by displacement, and you can therefore measure the amount of gas you've produced. Now, this is quite tricky to do, because firstly you've got to try and minimise the amount of water that's lost out of here if you want to get a good set of results. Then you also have to read very carefully. No matter how hard you try, you're always going to get a tiny little bit of gas up at the top. You're going to have to measure your starting volume, where your liquid level is starting at and where it ends up to, and calculate the difference. Now, also, it's quite hard to get the tube in the top here, and it's very, very fussy. It takes quite a lot of tries to get good at it. After teaching for a long time, I can do this quite easily, but it's still not as good as a gas syringe method. So a way to make this easier and better and more accurate would be to use a gas syringe. However, this way does serve just as well to measure the rate of reaction. So the second way of measuring the formation of a product is to look at the reaction between two liquids that react to form a precipitate, and you can measure the time it takes to form that precipitate. And again, a little reminder, that a precipitate is a solid formed in a reaction between two solutions, and that solid is opaque and insoluble, so it means that you can't see through the solution anymore. It blocks the transmission of light, and we're going to have a look at how you would do that experiment now. Now, how we can measure the formation of a product using a precipitate. Firstly, we take our solutions and we mix them together again in a conical flask, and this time we've got a bit of card, or a bit of paper, or a tile with an X drawn on the bottom in big black marker pen. And that way we can see it really clearly. So if we were to look down the top of the conical flask, down here, what we would see is this here. We would see a big cross in the bottom of our solution. Then we're going to time it. And what we're looking for is for the solution to go gradually cloudier and cloudier and cloudier. And eventually what we will see is that the solution goes completely cloudy, and when we look down our top view at the cross, we can't see the cross anymore. So you're actually looking for the point where you can no longer see through the solution. It's not going to go black, obviously. It'll be, often in the reactions, it's going to be a slight yellow colour. You will see nothing through there. At that point where you can't see it anymore, you stop the reaction, and that's measuring your product formed, because we're making a precipitate. We're not going to time from when we first see a precipitate, because that can be a little bit hard to see. You'll have different people going, oh, can I see it, can't I see it? But even here, you're going to have differences in the way people can see the X disappearing. So it's not always, sorry, dropping my pen, it's not always massively reproducible. But they are the three main ways of performing these experiments, and you are expected to know the rough outline of them and what kind of things you would expect to see. So to recap, the first one, we measure the mass of the reactants as a change. You're reacting, you're making a gas. The mass appears to go down because gas is escaping into the atmosphere. We're not losing mass in the reaction, the mass is still there, the gas is still in existence, it's just floated out of the reaction vessel and isn't being measured. If you could trap the gas into the reaction vessel, you would see the mass stays the same. The next method is measuring the volume of gas produced, and this can be done either with a measuring cylinder that's full of water and upturned in a trough of water, or a gas syringe. And here, you've got the issues that you could be losing gas could be escaping from various places. And then the last one is the precipitate forming, as we can see here. There are loads of good videos on YouTube that you can find which show these reactions happening. Sadly, because I'm not in a lab, I can't demonstrate them for you apart from drawing these diagrams. But hopefully when the lockdown is lifted, I'll be able to get some of that done for you as well. Okay. And the other way you can do the precipitate method is by using a light meter. And again, you get your reaction vessel, except this time you suspend it using a clamp stand, and you get a light meter underneath. And that way you really want to position it so it's actually touching the base of the conical flask. And as the light, as a reaction progresses, the amount of light that gets through to the light meter decreases, and the number that you'll see on this device will go down. So eventually this will go down to maybe like 0.25, for example, and you can monitor that, and you can measure the time and see how the light rate, so say every 5 seconds, 10 seconds, you record what the light meter says for its value in lumens or whatever the light unit is on your particular light meter. And this is a much more precise way of doing it than using the cross method. It's not relying on people's subjective opinions and being like, oh well, I think it's gone now, has it gone, maybe, yes, no, and then the kind of uncertainty that you will get in that experiment. There's only one real way that you'll learn about all those uncertainties, and that's to actually do it yourselves. So hopefully you'll get the chance to do that. For any practical, required or otherwise, you are expected to be able to create a results table and fill this in and work out information based upon this. So here is a sample results table. In column number 1, we've got our experiment numbers, so experiment 1, experiment 2, experiment 3, experiment 4, experiment 5. We've got our mass of product formed column, time taken column, and our rates column.
Now you should notice straight away that there's something missing from this table. Not the results, but something more important for our table before we start an experiment. Yep, that's right, it's missing the units. So you always need to make sure you put your units in your table. Again, this can cost you marks in the exam if you forget to do it. So get in the good habit of always making sure your units are in your tables, because then you won't make that mistake in your exam. So mass of product, grams. Time taken, seconds. Rate, which is mass divided by time, is in grams per seconds. So I'm now going to populate this with some made up data for some just random pretend experiment, and here's what the data looks like. So we now need to work out our rates in this final column. This is working out our mean rate, our rate for the entire experiment. Okay, and this is something that you need to be able to do. Everyone, higher and foundations here. So it's very simple. You've got to take the mass from the mass column and put it in where we see mass in the equation, rate equals mass. And then take the time and put it in the time slot, so mass divided by time. So in the first one, 53 divided by 12. The second one, 45 divided by 10, and so on. And here I've given the answers to two significant figures, so 4.4, 4.5, 12, 4.6 and 4.7. Now you may be asked to work out an average rate from all of these. So work out the average rate from all of these experiments. And you can see here there's an anomalous result in this set of results here. Can you spot the anomalous result, the one that doesn't fit the pattern? Yep, it's the 12. Okay, so we've got 4.4, 4.5, 4.6, 4.7. They're all really close together. 12 is very different. So if you were to calculate the mean of this in an exam, you wouldn't do 4.4 plus 4.5 plus 12 plus 4.6 plus 4.7 and divide that by 5. You would ignore the 12. You could even cross it out if you wanted, and then do 4.4 plus 4.5 plus 4.6 plus 4.7. Divide the answer by 4 instead of 5, and that would give you your mean. The next thing you'd be expected to do is be able to draw graphs of your results. Okay, and you should be able to interpret what those graphs mean. And for higher tier, you should also be able to draw a tangent on a curve and work out what the gradient of that tangent is. And that's useful for working out the rate at a given time, or the instantaneous rate. So it might ask you, what is the rate at 12 seconds into the reaction? And you can work out the rate at that specific time from that tangent. So, graph skills. On our y-axis we have the amount of product that we've made in grams, so don't forget to put your units on your graphs when you're drawing them, and time in seconds on the bottom. And again, you need to make sure you draw in the exams as well with pencil and ruler for your axis, and for indeed everything else should be drawn in pencil. It's not something I have the luxury of on a whiteboard. Now, you may get, for example, in your reaction, the reaction progressing like that. Okay, so you'd be able to say, for example, that the reaction starts off, it increases at a steady pace before it slows down and then levels off, the reaction stops. And we'll look at the reason why that is in a future video. You should also be able to compare that with a separate reaction, reaction 2, which I'll draw here in blue. And reaction 2 looks like that. So you should be able to say something different about that. So for example, it's made more product, this reaction. It's made that product in a quicker time as well. Okay, it's taken the same amount of time to make this product. If we have a look at the graph, it's taken the same amount of time to make the increased product compared to this one. So the rate must be faster. You may also see a graph which looks a little bit like, unfortunately I've only got the two colours of board pen. So I'll draw a dotted line like this. And again, this reaction is happening faster. So blue is fast, or faster, plus, a really bad pen, sorry, plus more product. Dotted line, faster, but same product, and the dark full line is original reaction. Okay, so you should be able to interpret those kind of graphs, be able to say things like there. So this is faster than this one because the gradient is steeper and it makes the same amount of product in a shorter amount of time, which is what the rate is. This one, you can see because the amount of product is a higher line, it's made more product. Okay, so it's done it faster and it's made more. You should also be able to work out a mean rate of reaction from a graph. You may be asked in the exam, work out what the mean rate is at 30 seconds. And say 30 seconds is here on the graph at this particular point. First step, get a ruler and a pencil, and you're going to draw a little dotted line following the lines on the graph all the way up till you hit the curve. When you've done that, you've hit the curve, you can go across here and read off the y-axis what your units are there. And say, for example, your units there are 20 grams. Again, then your mean at 30 seconds, or between 0 and 30 seconds, would be 20 grams divided by your time, 30 seconds, and that would give you your rate. You may also be asked to work out, for example, what is the average rate between 30 and 60 seconds. So say 60 seconds is here. Again, what you would do is we've drawn this one up here. We're going to draw again a second vertical line up to the line of best fit, and we're going to draw a line across. And say that says 40 grams up there. We'll go 30, we'll call that 30 grams. So we've got 20 grams and 30 grams. So we've got a change in set time of 30 seconds. We've got a change in mass of 10 grams. So we can work that out. Change in mass. So that triangle, delta being change in mass is equal to 30 take away 20, which equals 10 grams. And our change in time is 60 take away 30, which is equal to 30 seconds. Therefore, our rate, this little symbol means therefore, rate is equal to 10 divided by 30, which equals 0.33 recurring grams per second. Okay, and that gives you your average rate between there. The next thing we need to look at is how to work out a tangent. Now, you may also be asked at higher tier to work out the rate at a particular time. Now this is trickier. This requires you to work out the gradient of a tangent and to draw a tangent on in the first place. So say the question says, what is the rate of reaction at 30 seconds again? And we'll have 30 seconds is here. Okay, so there's our 30-second mark. And much like before, you're going to trace up to the line of the graph at 30 seconds and put a little mark on it this time. Now, that is our first step. So we've got our little mark on. I'm just going to make it a little bit bigger so it's more visible. Then you're going to place your ruler on the graph. But firstly, you've got to imagine where is the graph going at exactly that point. So you may want to extend the line a little bit before and afterwards. Where is it going between there? If you were to carry on extending that in a straight line, where would the graph line go? Okay, so I think it looks about there. So I'm going to place the ruler there. So you're going to adjust it so it's clearly not there because it's not touching your points that you've marked on. Neither is it there because it's not really touching the entirety of the point that it's on there. But about there for me on my graph.
and then you're going to draw, touching that line, a nice straight line using your ruler and your pencil. Okay. Now that's our tangent. That's the first step. We've drawn our tangent on our graph. Now we need to work out what the gradient of that tangent is, and this is actually quite simple. We're going to need a formula. The formula is gradient is equal to the change in y divided by the change in x. So y and x. Now, to work out what the change in y and the change in x is, you can use your graph paper and you can draw at an appropriate point a little triangle on your tangent. So let's make that about there, following the lines on the graph paper. So now we've got our little triangle, and this will tell us what our change in time is and our change in mass. So this is our y, change in y, this is our change in x. So change in x. Ooh. And you're going to have to count on the graph paper what that is. So say for example, this here, if we trace it all the way down, that takes about 10 seconds. And over here at the end, that's about 50 seconds. Then our change in x is 10 to 50. 50 take away 10. Really, really easy. That change in x is 40. So change in x there. So I can write that on there. It's 10 and 50. It's 50. Take away 10, which equals 40 seconds. Our change in y. So say here we've got 10. And here we've got 12. Our change in y is 12, take away 10, which equals 2 grams. And then it's exactly the same formula before. So rate is equal to mass, or the change in mass, divided by the change in time. So in this case we've got 2 for our mass, divided by 40 for our time. And our answer is 0.05 grams per second at 30 seconds. Okay, now that's quite tricky. The trickiest part of this, in my opinion, is figuring out the gradient, how to draw the gradients on. It will come with practice. I suggest you download some past paper questions and give it a go. Can be quite tricky if you don't have graph paper to do it yourself, because obviously on here I can't put the units on. But if you've got any questions about it, there are some really great videos about how to calculate a tangent or draw a tangent and calculate the gradient from those. You can go and check those out, or you can ask in the comments below and I will try my best to help out. Okay?
And the summary. So we need to know that rate is how fast the reaction is. We need to know that rate is equal to the change in product or the reactant divided by time. And this can be mass, it can be volume, it can be the amount of light that can be transmitted through the solution. The units are usually in grams per second, centimeters cubed or milliliters per second, or moles per second for higher tier. You should also be able to draw and interpret graphs from experimental results, so be able to say this reaction is a fast reaction, this reaction is a slow reaction, this reaction produces more product than the other one. And for higher tier, you should be able to draw tangents on curves and be able to work out the gradient of that tangent. The gradient of that tangent is the gradient at the specific time, or in other words, the rate of reaction at that instantaneous moment, that instantaneous rate of reaction. Okay, please remember to leave your comments down in the comment section below. If you've got any questions, please feel free to ask them. Please remember to like and to subscribe as well. That really helps me, give me the motivation to keep making these videos. I hope that you find them useful for revision and for learning while we're in lockdown. To my current year 10s, hello guys, I hope you are doing well. I hope you are staying safe and looking after yourselves and your families during this testing times.
For future Year 10s, I'm sure a pleasure to know you and a pleasure to teach you, and I hope you find this useful as well. Okay, take care guys, hope to see you soon. Bye bye.